So welcome if you've joined us online, or welcome if you've joined us in this space to this hybrid seminar this afternoon. My name is Marsha Neskerman. I'm the director of the Institute of Advanced Studies, and it is my very great pleasure to welcome today, as part of the IAS annual theme of Breathe, Professor Masashi Yamakawa, who has come to us from Kyoto Institute of Technology, and who has really made a very special effort to be here with us today. And we are enormously grateful to him for actually sparing the time, because it's been very quite complex in terms of the logistics, and we appreciate that and more than you can imagine. And I'm going to be turning over to my colleague Minsu Kim, who is going to be doing an actual introduction for this talk. So let me just do a few things, which is to say, welcome on behalf of the Institute of Advanced Studies. The Breathe theme, which is what we are wrapping up today as people are coming in, is a theme, the annual theme this year, and it's been one of the most extraordinary and interdisciplinary themes that we've had the opportunity to host here at the Institute. We have been thrilled to have scholars who are technologists, scientists, health scientists, people working on breathing from a point of view of the body, the point of view of the forests, the point of view of ecologies, rivers, and planetary breath, cosmological issues. But we've also had artists, designers, and a whole range of political theorists looking at this. So one of the kind of core issues around this has been not only how we understand breathing, breath, internal structures, the way in which we can deal with both the interior and the exterior and so forth in terms of breath, but more importantly, how we deal with questions around how populations breathe and how disparities in power and politics can often be the underlying issues that either constrain or enable the greatest technology to come forth. And we're really interested in those dynamics, and we are therefore really thrilled to be able to be talking to colleagues who are working at the cutting edge in fields around air quality, breathing, breath, and so forth. So with that said, I'm going to turn over in a moment to Minsu, but I really want, before I do that, to note for anybody who's joining us online that we have a Q&A and a chat button. You are very, very welcome to feed questions or comments during the talk into those functions. We will monitor them, and we will ensure that you're able to have a conversation before the seminar is over. The other thing I want to point out is that the slide presentation today, there's been a bit of testing around the slide presentation. It's quite data rich. So it sometimes is causing a lag in the sort of double zoom recording of it and projection of it. We are aware of that here. So if you're joining us online and it seems to freeze, we'll be aware of that, and we'll also be able to deal with it. So you don't have to panic, just stay online and it will be reproduced, and we'll catch up with the slides in due course. So there's no issue if your screen seems not to work for a moment. We've got that covered. And without any further ado, no more housekeeping. Minsu, if I can turn to you.
Thank you. Hi, my name is Minsu Kim from Mizuho School. It is my pleasure to introduce today's speaker, Professor Masashi Yamakawa from Kyoto Institute of Technology, Japan. Professor Yamakawa's major research area lies in the field of computational fluid dynamics, with a particular emphasis on conducting highly dynamic simulations using moving meshes. Since the COVID-19 outbreak and the subsequent pandemic situation, Professor Yamakawa used his knowledge and expertise in CFD to simulate viral particle transport in living environment. His substantial contributions and innovative approach has been garnered and widespread recognition from the media in Japan, and have also been acknowledged by Japanese government with 2 awards. And notably, 2 of his list of research papers were featured on the cover pages of the leading scientific journals. Today, Professor Yamakawa will share his research vision with us, and I believe this presents a wonderful opportunity for us to discuss our future research directions and visions together. Let us welcome Professor Masashi Yamakawa. Thank you.
Thank you very much for Dr. Kim. So today, the title of my today's talk is Computational Modeling of Virus Droplet Transport. So my major is computational fluid dynamics. So for governing equation, so approximate solutions are obtained numerically using computer. That's to estimate the result. So for example, we show the relation like this. Then my main theme, research theme is fluid simulation around a moving object. For example, you simulate a flow around the swimmer. You put the swimmer in the uniform flow like this. So it is similar to estimate the design of the car using the wind tunnel like this. Then on the other hand, my model is like this. So moving object itself occur the flow with the interaction between the fluid and body like this. Then so for special mesh, sorry, the surface mesh and special meshes, we use the unstructured like one, and the moving grid is expressed like this. To avoid the zero volume or crushed volume, we introduce a spring as a grid line like this. Therefore, using this moving grid, I compute flow around the body. So at that time, we introduced the moving grid final volume method. It is the bit different from the normal one. So when I plot the flow around the swimmer, so it is three-dimensional case, but in this case, we introduced the four-dimensional space-time unified domain. So totally, we solve the four-dimensional time. Then we need the complicated model coding, but we get the high accuracy simulation using this method. Then after them, there's a swimmer with dropping kick is swimming in the computer like this. Then this motion make a thrust and swim in the water in the computer. Then, so using this data swimmer, we can conduct the, for example, optimization of maximally bending angle. This is the speed for the time. Then the individual one is the maximum angle degrees. So when you get the high maximum angle, you get the high thrust, but it is make the big drag. Totally, so we have the best performance using, in the case of the using 65 degrees. It is the kind of the exam in this computer. And so digital film are not tired. So 24 hours can swim in the computer. So we can optimization in using the computer. It is one example. So for extend the another athletic sports, so we can extend it. Okay. Then I also use the I also proposed moving computational domain method. In this method, computational domain also moved according to the motion of the body. Then using this method, so for example, we can express the cornering like this, and also can express acceleration, deceleration, and we can release the limitation of the computational domain. For example, the very big truck, we can apply the calculation. Then this is the simulation of a tiltrotor aircraft with the flight mode. It's called the Osprey. Then so this is continuous simulation from the taking off to the flight. When the Osprey take off, the other takeoff mode, the downward should attack the ground, and after then, change the flight mode to change the direction of the engine nacelle. So this character is changed the helicopter to airplane continuously. So it is one of the example. Next is submarine, submerged under the water. In this case, the turbulence, rotor is turbulent with the submarine. And at that time, so we consider this is the surface that also changing surface calculating. This is a simulation of helicopter passing each other. It's a very dangerous case. It is difficult to examine reality, but in this computing, and this is moving MCD method, we can compute this type of the exam. Then this is the flying car simulation. It's in Japan, so one venture depicting this type of the flying car is called rotating octorotor type. Then the flying car also computed like this. We obtained just the speed, maximum speed and the highest. Another thing to compute thinking about the 8 rotors, independent rotation number, and finally, so the interaction of the rotation, rotor and airflow is decided the position and orientation. Sorry. Then this is the bicycle simulation. In this case, especially with the pedaling, and we can confirm the pedaling after the rating the behind of the flow upon the bend. And this is beating heat. It is left ventricle simulation. So today's topic is start. The topic is computer modeling of with droplet transport force. So my introduction. Okay, so motivation is Swift influenza pandemic in 2009. At that time, I considered, fortunately, I didn't become a catastrophe in Japan. But if the new strain of influenza was bird flu, so how do we get through the year until the vaccine is completed? As an engineering researcher, can I something using computer flow dynamics? Then I started the research on the virus infection simulation since 2010. The size of virus is about 0.1 micrometers. So so far, so the behavior of the micrometer is move with the airflow simultaneously. So, but at that time, I think so. It cannot exist virus. So virus is in the droplet usually. But then in the case of calculation considering droplet, we have to consider more evaporation, gravity, temperature, humidity, margin of droplet, drag, and so on. Then left-hand side is without consider droplet. So after coughing teacher, all wheels are spread in the classroom. But if in the case of considering droplet, after coughing, so heavy droplet, big droplet fall down in front of the teacher like this. Then maybe two or second or third person. So the droplet is spread. It is normally social distancing. So you can see the completely different from the so far one and my proposed one. Then I use this consideration to input the corona sorry. So this is the 10 years ago simulation. So it is for the full seasonal flu. Then this is infection simulation in the crowded train. The theme is what happens if there is an infected person in a dense place like this. Then at that time we use the personal computer, so there's no power, and the children and the adult is expressed as a small resource. Then this is a mesh, and in the train I put the sitting person. It is indicated sitting person, and the standing person, children, and finally we can express the crowded train like this. Then it is I adopt the Keihan Tohoku line. It is major line in the Tokyo area in Japan. The ventilation system is like this. And we put the 10,000 droplet over the passenger like this. Then this is the simulation spread the droplet around the door. So around the door, so there's small space from the passenger's head to the top, and the droplet is relatively easy to spread. Then finally, this area, 8 persons are infected. The infected person shows from the head of color from the gray to the purple. Purple indicates the infected person. On the other hand, in the droplet spread from the near the sheet, there's a little bit big space in the area. Then, so most of the droplet around in front of the sitting person. Totally, eventually 3 persons are infected. So from the 2 results, we understand that it is there's a high risk in the around the door, but it is one example. Next is respiratory tract droplet deposition simulation. The theme is what happens when you inhale the virus droplet. In the case of nasal breathing, this is the 5 micron diameter droplet is 15 micrometer. The red point is floating droplet, and the green point is adhering droplet. So we can see that bit different from the first one. And next is mouthing process. In the mouthing breathing, also the bit different. But we focus on the different from the nasal breathing and mouth breathing. In the case of 5 micron droplet we used, in the nasal breathing is around 30% of droplet out of body, and but some droplet put on the throat area, and on the other hand, the more than 80% droplet reach the lung. For example, so seasonal flu, in the case of seasonal flu, so the main receptor is exists in the throat. So in the when you nasal breathing, you tend to infect the seasonal flu. On the other hand, so the bird flu receptor is in the lung. Then you tend to infect the bird flu when you have a mouth breathing. So this is the simulation in diamond places. The diamond place is a big ship. So the theme is that airborne infection occurred. it is long term with droplet transport simulation. Purple color is more than 10 micron droplet. The red droplet is less than 10 micrometer. And big droplet fall down the floor or put the body. But less than the 10 micrometer droplet spread long range, and it may be so about 1 hour. So droplet is continue to spreading. So when start the COVID-19, we considered so airborne infection is occurred by this reason. Then so it is from the based on the PC. Then after April 2020, we start the supercomputer Fugaku droplet transport simulation project. Then a lot of laboratory, university, and company participated in this project. The following result is all based on the supercomputer. And first term is face mask. This is the infection prevention with face mask. The relationship between the filter correction effect of the mask material and the penetration performance was investigated by the exponential measurement. It is exponential measurement. This is the exponential measurement result. The filter concentration for filter pressure. For example, urethane is around here. It is very easy to spread. The cross is around there. The non-urban is around here. Relatively, so it is a good performance as a material. Then these results were used as a calculation condition for simulation. Using this result, we show the 5 results. For example, urethane, close to urban, and N95. Yellow droplet is emitted from the cap face and face mask. And red is adhered to the mask and face. And blue is transparent mask. So completely different from the behavior of the droplet independent of the material. Then these 5 results. After them, I several computation. The totally is here. The urethane is not good performance. The crosses depend on the cases. And finally, so non-urban is relatively good performance. So we recommend at the time we recommended the non-urban type. Then this is the infection prevent effect to the mask face. It is so two-factor extent can with droplet and aerosols be prevent from the entering the body with inhaling. So it is without face mask. It is the non-urban mask with face cap. We can see the so little bit confirm a lot of droplet inside the body. The quantitative evaluation is here. So upper side is without mask, lower side is with mask. Maybe 5, 15 or 14, less than 14 droplet are same result, but more than 5 micrometer droplet are different. So mask can prevent the entering the big droplet like this. The next theme is social distancing. It is comparison of droplet behavior during the conversation, singing, and coughing. This is conversation. This is singing. The behavior is the same, but the number of droplets is maybe 3 times of the conversation. Then, on the other hand, this is the too strong coughing. the spread distribution is different from the another one, but the total droplet is same to the singing type. And this is comparison of mask, face field, and mask guard. Face field, the lower, a lot of droplet spread lower. Mouse guard, in the case of mouse guard, a lot of droplet up past forward. Totally, mask is a good performance. And it is the effect of the face shield. This is the effect of protected droplets from the infected person. It is the effect not scattering droplet of infected person. So you can see the behavior of the droplet. Totally, so blocking face of splashing splashes is as expected. So aerosol maybe enter the gap. So next is the effect of the humidity on the droplet transport. 4 persons in the office, 1 infected person is coughing, and the humidity is 3% to 6% to 90%. The location of the another parameter is like this. This is the result of 30%, 6%, 90%. In the case of humidity, 30%, so small droplet reach the in front of the person, and in the case of humidity, 90%, a lot of droplet fall down on the desk. Then to focus this one, it is the number of droplets reaching a person 1.8 meter ahead, percentage of droplets generated by the coughing. So 3% is very big number. Dry accelerator, develop aerosolization, especially when the humidity is less than 30%. And the effect is remarkable, and it is necessary to control the humidity. This is the effect of the distance of the droplet transport. We tried the rate 0.8 meter, 1 meter, 1.2 meters. So this is the result. You see the same result. You see the same result, but so to focus this result, it is the number of droplets reaching the person directly in front. We checked the 0.8 meter, 1.2 meter. Very narrow cases are tried, but so result is different. So droplets rarely reach neighborhood when facing straight ahead, especially when the distance less than 1 meter. The number of arriving droplets, 1 meter, the number of arriving droplets increase rapidly. Maybe just the 40 centimeter difference. So the droplet is maybe 8 times or more. This is the case of talking while walking at 44 meters and standing case. So standing and walking, the droplet spread distribution is different like this. And this is comparison of speed, 2.3 kilometers, 4.4 kilometers, and 9.2 kilometers walk. So almost so individual, independent on the walking speed. So the distribution of the droplet is different. Then compared to the normal conversation while standing, the behavior of droplets are aerosol during the walking and exercising is markedly different. When walked, there is a distinct area where droplets tend to concentrate, which is larger than observed during the critical conversation while standing. Additionally, the size of this concerned region increases with marked walking speed. Next is various situation. It is droplet infection risk assessment in an izakaya. Izakaya indicates Japanese pub. in izakaya, distance between the people is often less than 1 meter, which increases the risk of the infection. In total, maybe so this time is normally used. Talking for about 1 minute, this is the condition of the simulation. Speaking 1, 2, 3, from 10 to 10 in English in 45 seconds and repeat. Able to changing the number of droplets arrive due to the difference in sitting location. This three result is different to the direction to the speaking. This is for front, for diagonal, and this is the beside. Then, okay. This is the result. This is the number of droplets reaching the persons in front. This is the diagonal and next. So vertical measurement is different. So for the straight, maybe 5% of droplet reached. The diagonal direction, maybe 1% around. But neighborhood, so around 30% of the droplet reached. So droplets have the relatively strong linearity and hardly reach anyone other than the person who spoke to the people. Highest risk of infection from the next door, this one. And this is the droplet infection risk assessment and the countermeasure in the restaurant. It is modeled as a small restaurant in Japan. This model has the ventilation outside air supply and ventilator exhaust. The door gap air supply and door gap exists, and air conditioners here, it is circular type. Then we compare the air conditioner on and off. So when the air conditioner is turned off, the indoor air quality becomes uneven. To disperse the risk of aerosol scattering in room, it is important to actively use the air conditioner to steer the air. And this is so, in this restaurant has the kitchen exhaust fan here. This is comparison the fan on and off. So the red air is dirty air and blue air is fresh air. The exhaust duct in the kitchen is powerful and can increase the ventilation frequency per hour by about 4 times. This is in the classroom. It is this assessment of aerosol transmission in the public school. The public school, so typical air conditioner is set, but the main ventilation is opening the window. So we tried the 4 cases. Yes. So in this case, so white is the dirty air, and the dark blue is the fresh air. After 6 seconds, this type is the good performance. In this case, so window is 20 cm open and door is 40 cm open. So fresh air includes from the window to the door. And this is this assessment and countermeasure in the outdoor activities. So maybe 10 people standing around the barbecue table. The distance from the first person to 1 meter, this is the 1.7 meters. And he is infected person. He is infected person. He spread the droplet for others like this. This color indicates the reaching number of droplets. So this is the a lot of droplet, residual droplet. So the risk located in front of the infected person, the number of arriving droplet can be reduced by about half, extending the distance from the 1 meter to 1.7 meter. This is the simulation of the multi-purpose hall. It is just to demonstrate of a supercomputer. In this simulation, we put a real shape human, 2,000 human, 2,000 persons put on the air hall. Then we solved the individual persons' heat and around the air to all relation. And this is the result. It is a ventilation of this multiple hole. It's just a demonstration. The next is convergence. It says infection control on the crowded terrain. And this crowded terrain is different from my PC's one. We use the complete shape, human, and the restriction in the detail. The evaluation of ventilation effect of the opening window and opening door in the train. The speed is 8 kilometers. Passenger is around 230. The air conditioner is installed. And this is the lining case. This is the stopping case. Sorry. Open and close the door processed like this. It is comparison of the closing window, open window 10 centimeter, 20 centimeter. So ventilation in the car is promoted by the opening and window, while the ventilation progress from the center of the top of the car to the rear. The front air is somewhat stagnant. And this is the ventilation by opening and closing the door. Train stopping at the station. The ventilation began started again after the closing the door, approaching the result of opening the window by 5 centimeters. It is infection control on airplane. I make the model as a Boeing 787 economy class like this, and the ventilation system is also like this. The red color is the dirty air, and the blue color is the fresh air. It is evaluation of ventilation performance. In addition to outside of ventilation, the HEPA filter, so Boeing 787 cases filter also remove the wheels from the air circulation system inside the aircraft, so that inside the aircraft is published in about 3 minutes, very clean in the airplane. Then this is the infection control in a taxi, Japanese taxi. This model here, it is Japanese typical type of taxi made by Toyota company. So it is evaluation of ventilation performance and activity of countermeasures such as opening windows and partitions. So taxi speed is 4 kilometers and passengers 3 persons, including the driver. And in this case, we computed not only the inside but also outside of the car. It is evaluation of ventilation performance. The ventilation progress from the front seat side and rear seat side. It becomes almost uniform in the 30 seconds. Replaced with the fresh air about 2 minutes. It is droplet scattering when the driver coughing and its measurement. First countermeasure is all window closed. It is a normal case. The aerosol, in the case of all windows closed, aerosol spread rapidly throughout the interior of the vehicle due to the strong flow of the air conditioner. And first measure is driving seat and the left seat window open. This window and this window is opened. So in this case, approximately 1/4 of the droplet are discharged from the window after 20 seconds. The third is with the partition. So by partitioning and opening window and droplet, effectively expelled to the outside after 20 seconds, the droplet halved and amount of droplet reached in the rear seat is also reduced. This is the infection control on the schedule fast. We check the two cases. First case is stopping bus. Bus is stopping in the bus. Speed is 0. Side window is closed. Door open. Door is here and center here. And the air conditions on and the ventilation fan also on. On the other hand, in the case of the driving case in the city, speed is 20 kilometers. Tires is open. Door is also closed. Air conditioning and battery system is on. This is result almost same, but in the stopping bus cases, rear area of the bus is not good for ventilation. Okay, the final theme is infection risk simulation. It is infection probability calculation method. This is infected person. This is evaluator. This is sampling box. The small box is put around the mouse here. A sampling box is installed the evaluation void. Not moving the person. So put the sampling box to evaluate the distance from the infected person. Then the number of virus contained in the droplet is set. At this time, we introduce this number, this figure. And the number of virus entering the body through the breathing is calculated by simulation. The number of viruses leading to infection is estimated from past cluster event. Cluster event is there. From this event, this paper indicates the number N0. So it is the border of the infection. The number of viruses leading to the infection estimate, and probability of infection is calculated by the following equation like this. Then this is the behavior of the droplet. In this case, is repeating 1 to 10 in English for 9 seconds, once in the middle with loud voice. Okay. To see that this figure, it is probability of infection for distance from the infected person. For example, you stand in front of the infected person just 1 meter, and the infected person speak loudly, your probability of infection is maybe 22%. But if you move more 1 meter, so you stand in front, you stand in front of the infected person, you have a 2 meter distance. In this case, your probability of infection is less than 10%. So this is indicated the probability of the infection. Using this consideration, we put the restaurant. So risk assessment, the control measure in the small restaurant. The restaurant is showed the previous slide. I skipped the detailed equipment. So In this simulation, there's 16 persons in the restaurant, and all persons speak and spreading the droplet like this. And this is the supply dust, and this is the exhaust dust. Main airflow is from the blue to red line. Then some droplet is out of the restaurant through this duct. You see some droplet move to this direction. And this is the total package of the probability of infection. Okay, so the number is the person indicated. This is the infected person. This is the at risk person. Risk person ID and risk. For example, 70.7 indicated that from the 4 person to the 2 person, from the 4 person to the 2 person, so infection risk is 70.7%. On the other hand, 1.3 is the 2 to 4. Sorry, 2 person, 2 to 4 person. If 2 person has infected, so 4 persons infected by the 1.3% probability. But all persons I calculated, it is the all the result. The infection risk persons, when the infected person stayed in 1 hour is 2.3%. It is average of this room. In this situation, so in this, you don't know where is the infected person, but we have to want to know the risk of this room. Okay, so this is the average. It is important parameter. The 1, 2, 5, 6, 7, 1, 2, 5, 6, 10, and 14. 14 are the risk, high risk of the infection. Okay, the 3, 4, the 3, 7, 8, 9, 15 have a high risk of infecting others. It is up one side in indoor. Increase up to 78% depend on the positional relationships with the infected person. Then it is countermeasure. Turn on the conditioner and kitchen duct. Kitchen duct is very strong exhaust performance. Then, okay, you know the different distribution, this one and this one. So using the turn the computer condition and air conditioner and duct, so distribution is changed. The per capita infection risk decreased from the 2.3 to 1.9. So droplet spread over the wider area, but diluted, which was the effect to this spreading risk overall. So the word may increase local risk. And second countermeasure is partition. And there's seven partitions put on the restaurant table. The result is completely different to this one or this one. So you can reduce the red area. So average per capita infection risk drops significantly from 2.3 to 0.5. So reduce the risk infection of all, and some high risk geometric relationship remain. So it is sorry. Thank you. Sorry. That's all. Thank you very much for your attention.